Now let us see what happens when you apply a bias. Okay, so what we are going to do is that, okay, we are going to vary the bias all the way from negative and we are going to also, it's like we are going to going from negative minus V to plus V. So we again start with an n-type semiconductor. We again going to start with the n-type semiconductor here. So so this is a flat band. Okay, so this is our reference. Okay, so this is a reference. You can see the bands are flat, but to make this flat, okay, so you have applied some voltage here. Okay, so if you look at this one, so we have applied this voltage. So you had applied this voltage. So earlier this EF and this EF was same. Okay, so since this side has gone down, okay, this side has gone down, that means you have applied some positive bias. You remember we have gone down from here to here. Okay, that means VG should be positive. So for example, and so from this case, okay, if you are going to this is VG. Okay, so if you keep positive, okay, so now if I try to apply further, if you keep on increasing the VG, okay, that means this VG is further. If VG is greater than VFB, okay, then what happens is that you are trying to pull this further down. Okay, so now you can see from this case, this band is bending downwards. Okay, it's trying to follow the VG. So here it was flat here. Okay, now you can see there is a bending inside the oxide and there is a bending in the center semiconductor. So that means there is a field here. Okay, there is a field here and there is a field here. Now what is going to happen is that when there is a band bending here, now what is going to happen is that this is bending down, but the Fermi level is holding there. Okay, the Fermi level. So compared to this case, okay, compared to this case, what happens is that the EC has gone down. Okay, EC has gone down and is closer to EF now. So the conduction band is coming closer to the EF. Okay, if you go back to your the band diagrams here, that means so as the EF comes closer to the conduction band, then means the electron concentration increases, right? And similarly, if the delta between the EV and the EF is, that means the whole concentrations are very large. So that's the same thing happening here. So when you increase the bias, okay, the conduction band is coming closer to the Fermi level here. So that means, so you have more and more electrons near the surface. So you have suppose this is the electron concentration, the substrate, and this is this. So this N is now becoming much greater than N0, right? So this condition we call it as accumulation. So you are trying to accumulate the surface. Okay, you are trying to accumulate the surface with the majority carriers. So this is an N-type substrate. So the majority carriers are N-type. But what you are doing is that you are increasing the concentration at the surface, right? See, main thing is that, okay, here you are not changing the concentration by doping. Okay, so you are not changing the doping. You are changing the concentration of the carriers by modulating the gate voltage. Okay, so this is a principle of MOS. Okay, so that is that is why they are called field effect transistors. Okay, you are modulating the electron concentration by applying a field. So depending upon whether you are applying a positive field or negative field, okay, you are modulating the surface concentration. Okay, so in this case we are accumulating the surface. Okay, your electrons are being accumulated at the surface. Okay, let's go to the other side. Okay, so in this case, okay, we are going to apply negative VG. Okay, so the VG is negative. Okay, this is VG is, so we are going to apply negative VG here. So from this case, so we are going to increase. So when you apply negative VG, the Fermi level moves up. So here what is being happen is that, okay, so as you can see here, when this side moves up, the oxide also tries to move up, the semiconductor also try to move up. Is that clear? So here let's there's something else is happening here. So here the position of the Fermi level is continuous here because there is no current flowing through the system. Now in this case, your conduction band and the conduction band here, the valence band here, the intrinsic level, they are moving. So if you look at this point, okay, so this EC is moving away from EF. Okay, EC moves away So EC is moving away from EF. That means it is the electron concentration. The electron concentration is going down. Okay, so suppose this is N0, then surface E now is less than N0. So so when you are by applying a negative bias in this configuration, what you are doing is that you are reducing the electron concentration at the surface. Okay, so you can think one other way to think is that, okay, you can see that the field or the field profile, the field at the surface is not favorable for electrons. Okay, the electrons are being repelled. Or other way is that if you put an electron here, what is going to see is that, okay, it will just flow down here, because in the energy landscape, okay, it is just going down the valley. So if whatever the electrons, so these electrons cannot stay at this interface. Okay, so whatever it will move, follow down. So the surface, whatever the interface concentration of electrons, they are going down. So we call this such conditions are known as deplete. Okay, that is the surface or the interface is being depleted by electrons. What happens? Okay, so what happens if you keep on reducing the gate voltage? Okay, that is you are reducing the gate voltage. So that is you are moving this VG further higher. Okay, further high. That means there is a large. So if the gate voltage is very large, you can see the band bending is very large. The band bending in semiconductor is also very large. Okay, now this interesting thing happened. So now what is happening is that, so in this case you are the intrinsic level is coming closer and closer to the gate. So and for some gate voltage, the intrinsic level starts to cross the Fermi level. So if you look at the dull, so this is EI is above EF, but now in the interface EF is here, EI is here. So but this is okay. So this is a P-type. So this is like a P-type case. Sorry, this is like an N-type. This EF. So the EF is above. Sorry, I think this is EF. So this is N-type. Okay, this is N-type. EF is above EI, but here in this case the EI is above EF. Okay, so this is like P-type. So that means, okay, so this surface condition is favorable for holes. Okay, that means that you are changing the surface profile from an electron rich material to a hole rich material. Okay, so what is showing here, the surface you have a lot of holes here. Yeah, this is electrons here. So this condition we call as inversion. Okay, it is as if you are trying to invert the condition. Okay, so you are trying to invert an electron rich material to a hole rich surface. So this is known as an inversion. Okay, so the surface becomes P-type. Okay, so surface. So keep in mind. Okay, so this is not like doping. Okay, doping you are. So if you remove the gate voltage, okay, it will go back to your original N-type material. Okay, so this is a field effect. Okay, this is not modulated by doping. This is modulated by the electric field. Okay, that means you can change the electron concentration or the mobile carrier concentration from all the way from an electron rich material to a hole rich material. Okay, so this term is known as inversion. So the beauty of this MOS system is that, okay, you can go from all the way from accumulation to inversion. Okay, by just varying the gate voltage. Now let's similar thing. Okay, so that was through what we did is we took an N-type silicon. Okay, so similarly we can do the same exercise with a P-type silicon. Okay, P-type silicon. So in this case, okay, so in this case again what we do is that, okay, we start from a flat band case. Okay, so this is a flat band. Okay, so this is EF is here, this is EF is here. So we applied some voltage here. So this EF, okay, so now what is the nature of the bias here? This EF is above this EF. Okay, that means this whatever the VFB is negative, it should be a negative voltage. Then similarly, if we keep on increasing the negative bias, okay, if you keep on increasing the negative bias, so what happens is that, okay, we go from the same condition here. So this is known as accumulation here. So we keep on increasing then the field inside the gate. Okay, this is the field equal to 0 here. The electric field is equal to 0 here and 0 here. When you keep on increasing the bias, what is happening is that you are going to you are going to induce band bending inside the semiconductor as well as inside the oxide. So you can see now in this case your valence band, okay, your valence band is coming closer to the Fermi level here, or the gap between the valence band and the Fermi level is here and the gap is smaller here. That means you are increasing the hole concentration. Okay, you you are increasing the whole concentration of P, the whole concentration here. So this P is much greater than P0. Okay, suppose the substrate this is P0, you are enriching, you are increasing the surface concentration of the whole compared to the bulk concentration. Okay, so again, okay, so your accumulation, okay, this condition is known as accumulation, because whatever the majority carriers, you are increasing the concentration of the majority carriers at the surface. So this condition is known as accumulation. So for accumulation, so you are applying a negative bias here. You are keep on increasing the negative bias. On the other side, what happens is that if you start applying, if you go for the positive VG, what happens is that, okay, so here you apply VG negative, that means, so if you apply positive VG, that means you are going to pull this part down, pull this metal side down. Okay, then what happens is that, okay, the band bending, okay, from this one, okay, the band starts bending down. Okay, it tries to follow the gate bias. Okay, so if the gate goes down, the oxide and the semiconductor, it tries to go down. So you can see, now you can see for this case, for some cases, okay, so this is the EI and this is the EF. Okay, so this delta is this much here, this delta is small here. Okay, that means the amount of holes, okay, amount of holes is being reduced at the surface compared to the bulk. Okay, so this is known as, again, called as depletion. Okay, so this is known as depletion. So if you keep on increasing the bias, what happens is that, okay, so you keep on, okay, this is for a large positive VG, okay, for a large positive VG, what is happening is that your intrinsic level, the Fermi level is still continuous because there is no current flowing through the system. Your EC, EI and EV, okay, both bends down. For some biases, the EI bends so much that it goes below EF. Okay, so it goes below EF. So this EF is above now EA now. That means, okay, it's like an N-type semiconductor. Okay, but its bulk is still P-type. Okay, so what you have made is, okay, so this is the condition. Okay, this is the inversion case. Okay, so you have inverted the surface. So from a bulk material, okay, from a majority carrier, this bulk is lot of holes. So you have applied a large voltage, large positive voltage, such that the surface condition, again, is inverted. Okay, so that is inverted. So you have a lot of electrons here. So this condition is known as inversion. Okay, so the beauty of the, let me repeat, okay, the beauty of the MOS system is that, okay, you can change the carrier concentration. Okay, you can change the carrier concentration by applying a bias. Okay, so you can utilize this property that is being used in transistors. Okay, transistors, when you switch the transistor from off to on state. Okay, essentially this is what happens. Okay, the transistor may go from here to here. Okay, so this is maybe off state. Okay, it may be somewhere here. Okay, it may be somewhere here, off to on state. Okay, so you are essentially moving from a depletion to inversion, that's what the switching does. Okay, so you are from off to on, like this one. Now the question is, okay, where does these electrons come from? Okay, so when the gate gate voltage is changed, because if you are an engineer, the gate voltage is under your control. Okay, you can if you apply a supply voltage or something, variable voltage supply, so you can vary the gate voltage as you wish. Okay, but where do you get all these electrons and holes? Okay, you cannot just order them electrons and holes here. So this is these electrons here. Okay, where does this electron? Because in the earlier system, the number of electrons were very small. Okay, so for example, let's assume this is doped Na. The whole concentration is equal to P is equal to Na. Let's assume all of them are ionized. So electron concentration was Ni square by Na. So this is so if you do some math, right? For example, if Na is equal to 10 to the power of 16 and Ni is roughly equal to 10 to the power of 10. Okay, so that means electron concentration is roughly around 10 to the power of 4, right? 10 to the power of 4. But when you invert, okay, so when you invert, okay, you are converting from a p-type material to an n-type substrate. Okay, so it goes from 10 to the power of 4 to 10 to the power of 16. Okay, so it's a large change. Okay, so the electron concentration is increasing from 10 to the power of 4 to 10 to the power of 16. Now the question is, where does this come from? Okay, so it comes from something as thermal generation, or in a MOS capacitor it comes from thermal generation. Okay, so it has to wait. Okay, so because at any temperature there is both generation and recombination is happening. Okay, so but so all these electrons, okay, it comes from thermal generation. Okay, the fields are favorable such that So normally what happens is that if there is an N and P generation, okay, it may recombine back. Okay, so that's how it's at equilibrium. But here the fields are favorable. Okay, it may separate the electron and hole such a way that okay, there will be a large electron concentration at the surface. Okay, so let me stop at this moment and I can take some questions. Okay, then we will continue. Okay, so there is a question. So why is there a band bending in the vacuum level being the space is same for all? Okay, that's a very good question. So if you go back, okay, so this one, right? Okay, so this is a usual convention. That's a good question. Okay, so you can see, so this is as if the vacuum level is going down, right? So that's a very good question. So this is a usual convention. So ideally, what is being happen is that okay, this is the semiconductor here, okay, and we are moving inside the metal here, okay. So or from metal we are going inside the semiconductor, right? So ideally, there is no vacuum here actually. There is no vacuum here, but we are drawing. So this is mostly referring to a surface, okay. So that is why if you go from metal to semiconductor, okay, this so don't assume that okay, it's a vacuum is the same, okay. So we are not if we are going inside the semiconductor, there is no vacuum there, okay. So but this is how the convention is, okay. So normally it is refers to the close to the surface here. Okay, so what will be the okay? So next question is what will be the intensity of electric field in an N-type semiconductor at interface? Okay, so the amount of electric field, okay, we will see the calculation, how to calculate the electric field. The amount of electric field, okay, it depends upon couple of things, okay, it depends upon the applied bias, okay. For example, if a couple of the applied bias, it depends upon the doping and it depends upon the phi ms. So all these things it depends upon. So maybe we will see how to calculate. Okay, we will come to that. Okay, how to calculate the electric field intensity. So it depends upon these parameters, the applied bias. It depends upon the oxide thickness. It depends upon the semiconductor doping. All those things. So we will see how to derive some expressions for the electric field. Okay, so there is one question. Will there be any gradient in Fermi level after the application of voltage due to charge accumulation? Yes, there is no gradient in the Fermi level, because if for any gradient to exist, okay, in the Fermi level, okay, that means any gradient in electric field means there is a current flowing through the system. Okay, but in this system there is no current flowing through this, because the oxide is preventing the charge transport between the metal and the semiconductor. So that is why the Fermi levels are flat both in metal as well as in semiconductor. So you can see in this case, if you look at this one, okay, so this is Fermi level is continuous here, and similarly even if you go all the way from accumulation to inversion, okay, so you can see the Fermi level is drawn flat both in semiconductor as well as in metal. So that shows, okay, so there is no current flowing in this direction. So why is it the oxide, the thick insulator is preventing this one? Yeah, but what may happen is that if you employ a very thin insulator, okay, but if the oxide thickness are very small, okay, so what happens is that in such a system, what may happen is that these electrons, okay, these electrons, if you are heard about something known as tunneling, okay, these electrons can tunnel through this barrier, okay. This tunneling, okay, so this tunneling can happen, okay, that means there is a current flowing through the system. So let us assume the case the oxide is very thick, okay, so for that the oxide has to be less than 3 nanometer or something, okay, for that, or you need to apply very large bias, okay, for even then your oxide thickness has to be less than 10 nanometer. So for simplicity, initially we assume the oxide is thick so that there is no current flowing through the system, because the tunneling current, those the transport phenomena, they are different. So any charge accumulation or inversion, okay, that doesn't change the Fermi level any gradient, because for the gradient to be present, okay, you need to have the current flowing, because there is no current flowing through the system here. If there are no further questions, we can continue. Okay, now let us recap. Okay, so this condition for the condition we saw here. Okay, so this is the first condition we saw from this is a flat band condition. Okay, from here we are going to accumulation. So this let's put the p type and n type in the side by side. Okay, so this was the first case we took. This is n type. So here you can see the EC is coming closer to the Fermi level. So you can see depending upon the position of the Fermi, so the Nx, okay, so this Nx is proportional, is equal to some Ni or something EF minus EI by X by KT, right? And this EI is a function of, so it's proportional to the exponential of EF minus. So EI is a function of X. So you can see EI goes down or this delta is increased. So if this EFI minus EI is very large here, that means the electron concentration is very large. Okay, that means the electron concentration is something like this one. Okay, this is the bulk concentration, then the electron concentration increases at the surface. That is why it is called accumulation. So similarly, in the case of p-type material, so you can see this is the EF and EV here, and this EF minus EV close here. It's very small, the gap reduces. That means the whole concentration, okay, the whole concentration also very high. So the whole concentration is higher at the interface. It's a higher. This is a bulk concentration. Whatever the bulk concentration. Okay. So so even if there is a charge accumulation, okay, you can see there is a concentration gradient. Okay, so there is a concentration gradient from this side to this side, right? But there is no, but it cannot flow. It's not flowing because there is a field. Okay, there is a field here. So this field, okay, so this field actually is opposing the whatever the charge. So you can see the holes are accumulated here. That is because if you look at the potential diagram, okay, the whole energy increases in this direction. So this is like a potential well for the holes. So that's why the holes are accumulated. The holes will try to be at the lower energy. Okay, so they will try to come here. Okay, there are a lot of holes. So even though there is there is a large concentration gradient in the holes, okay, it cannot flow because the field is not favorable. Okay, field actually opposes the flow of electron holes here. That is why there is no net current here. Okay, even though there is a gradient. Okay, so don't assume that wherever there is a large concentration gradient it can flow. Okay, that is if the field is opposing the diffusion. Okay, so that means the net current is equal to 0. So the total diffusion plus drift, okay, whatever, it should be equal to 0. This is equilibrium. Okay, so that is why there is no current here. So this is about accumulation. Okay, the surface is accumulated. In the accumulation condition, the surface is accumulated with a majority carriers. Okay, this is in accumulation. So this is an p-type material. Okay, so the majority carriers is, so here in this case the EF is closer to the EV. So these holes are the majority here. Okay, so you have more holes here. Okay, more holes. So here it is electrons here, and here you have more electrons here. Okay, so keep in mind when you hear the word accumulation, okay, accumulation is means majority carriers. Okay, so you are increasing the concentration of majority carriers. On the other side, okay, if you so this was V is less than 0, V is greater than 0. Okay, if you think p-type material is easier, okay, let's track with the p-type material. So here the voltage was negative. Then if you apply a positive bias here, okay, if you apply the positive bias, okay, this is EF here. You are applying positive bias means the Fermi level goes down here. Okay, goes down here. The bands try to bend in the downward direction. Okay, it tries to go along with the gate voltage. So now you can see what is happening. The EV is moving away from EF. EV is moving away from EF. The EC is coming closer to the E. So or the EI is coming closer to the EF. Okay, for let's assume this EF and EV. In this case, so this gap is, so the whole concentration is exponentially proportional to, how is it written? Okay, so this is EF minus EI of X. So EI minus EF of X by KT. So now you can see this this EF. So here this gap was large and here is reduces. That means you are reducing the whole concentration. So P of holes is now less than P of P0 at the bulk. So you are reducing the number of holes at the surface. So that is why it is called depletion. So depletion means you are trying to deplete the surface. You are trying to deplete the surface with the majority carrier concentration. Okay, so whatever this mobile carrier is, so it is being depleted. The surface is depleted. Okay, same thing has happening for an N-type case also. So in this case, yeah, your EF is continuous here. So it is the EC moves up here. So that means you have less number of electrons here compared to the substrate. So that is why this case is called depletion. Then if you move on to something known as inversion, okay, so if you keep on increasing, so this was positive bias, if you keep on increasing the positive bias, okay, that is if you have a that is similar to an n-channel transistor, or we will come to n-channel. So here you are applying more and more positive bias, okay, more and more positive bias. Now we have reached a case where the EI has crossed down, okay, it has gone down below F, okay. So that means, okay, the substrate is p-type, okay, there are holes here. So whenever if the EI is above EF, okay, that means electrons here. So depending upon how much it is above, okay, that will depend upon the concentration here. So this is an electron here, okay, so similarly the electron concentration increases in this direction. So here this is very, so we did some numbers, okay, it is like 10 to the power of 4, okay, but here it is going up to 10 to the power of 16. So there is a lot of concentration gradient here. Again, similarly, you can see there is a concentration gradient, okay, but it cannot flow. That is because, okay, this is like a potential well, okay, this is like a potential well, these electrons are something like a trapped here, and there is a field here, because there is a band bending here, there is a field here. This field opposes the tendency of electrons to flow out of this well, okay, that is why this is net, there is no current, okay. So even though there is a concentration gradient, okay, so the existence of a concentration gradient is not a sufficient condition for a current flow. Okay, it depends upon if there is a field and if the field opposes the tendency to flow, that means the net current could be 0. Okay, and this system is still under equilibrium. Okay, that is why there is no flow. So this condition, okay, this condition is known as inversion. And similarly for an n-type material, okay, so if you look at the n-type material here, you are applying a large negative voltage here, okay, this is positive voltage here, you are applying a negative voltage for the system, the bands move up. Now what happens is, so here the bulk constant is an n-type material, so here you have electrons here. Now your EI went above above EF, okay, that means it's